Alright, 8.6 is basically all about 4 theorems. Now, on your, or in your packet that we did last class, okay, you actually used one of these theorems, or you should have. Okay, and you've been using some of them and you haven't really known that you were using them. Yes, it is. Okay. So on 8.6, we're talking about proportions in similar triangles, or and similar triangles. Okay, and the very first thing that we're going to come to is a theorem called triangle proportionality. Okay. Got your pink sheet? This is one of the theorems that you've probably already used. Okay. It's counting time, right? It does look different, doesn't it, Taylor? Okay. All right. You've probably already used this. Okay. And I'll explain why and how and what you got to be careful of after we do this. Okay. But it says if a line is parallel to one side of a triangle, and intersects the other two sides, then it divides the two sides proportionally. Okay. The diagram to go along with this is going to look something like this. Now, do these two lines have to be parallel for this to work? Yes. Okay, and that's where in the past you guys have been using this, but it didn't show the lines were parallel. You could have went through and proved it if you want. Okay, so we hadn't actually learned that you could do this, but I wasn't going to tell you guys not to do it because it is true. Okay, but we'll talk about that here in a little bit as to what we were doing. Okay, so I have this triangle. If those lines are parallel, then I can say that AB over BC
Excuse the interruption. Can I have Austin Sanders to the office for just a moment?
Yes.
Thank you.
That has to be equal to ED over DC. Have some of us been doing that already? Technically, before right now, technically you should have been doing BC over AC. You guys see that? because BC is the whole side of the triangle, and so is AC, right? Of my two triangles. Technically, before now, you should have been doing that. Okay, but if these two triangles were similar, okay, BDC and AEC, wouldn't this be true anyways? Yeah, so some of you were getting away with using this, okay, but you do have to be careful, because if those lines aren't actually shown that they're parallel, okay, maybe you can't prove that they're parallel. Okay, so in that case, this proportion wouldn't work, right? Okay, so just be careful. Make sure your lines are parallel. If your lines aren't parallel, you're probably going to want to do the entire sides of the two triangles. Okay. We're going to kind of go through these theorems as quickly as possible because they're not super difficult. Okay, the second one is the converse of that. So it's the converse of triangle proportionality. The last one said if the lines were parallel, then we could set up that proportion, right? So the converse is going to say what? If that proportion is true, then the lines are parallel. Okay, so if a line divides two sides of a triangle proportionally, if a line divides two sides of a triangle proportionally, then it is parallel to the third side. If a line divides two sides of a triangle proportionally, then it is parallel to the third side. Same exact diagram, except now I don't know that those two lines are parallel. Okay. So I do know though that if AB over BC equals ED over DC, then what must be true? Then AE would be parallel to BD. Good. How do I know if this proportion is true? What would I be looking for? How would I be able to show that this was true? I think you're saying the right thing. If these ratios were what? The same. That's what you're getting at, basically, right? Okay. You would set up these ratios, and they had better reduce to the same thing, right? That's how you would know if those were equal to each other. Okay. I'm not going to go through and actually set up and solve example 1, but let's just talk about it real quick. So is everybody looking at example 1? Okay. On example 1, the lines are already parallel, correct? Could I find the length of CE? Yes. Ryan, what proportion would you set up to solve for CE? Do the numbers for me, please. Okay. 4 over, which would be x, right? So you can do 4 over x equals 8 over 12. That would be one option. Would somebody else do it differently? Seth would have. Okay, that's fine. There's a lot of ways you could do it, right? Okay, so just be aware you could set that up and solve. Okay, would it be okay in example 1 for me to do this? Yeah, it would. The x comes from CE, right? Which is the whole right side of my small triangle. The x plus 12 comes from CA, which is also the whole right side of my big triangle. Right? Everybody with me so far? The 4 comes from the whole left side of my small triangle. And then the 12 is the 4 plus 8, which is the whole left side of my big triangle, right? Okay. You don't have to do this anymore if the lines are parallel. If they didn't tell you the lines are parallel, would this have been the proper route to take? Yes. Okay. Just remember there's multiple ways to set up each one. Now, I want to take a look at example 2, but I'm going to do one that's not in your book because there's a little extra discussion I want to talk about here. Okay, so I have A, B, C, D, E. We want to know, are those two lines AB and EC parallel? They tell us that this is 9, this is 24, this is 26, and this is 9.75. That threw a twist in it right there at the end, right? Because how am I going to set up ratios and understand if they're the same if there's a decimal? Okay. Well, first of all, I know for those two lines to be, be parallel, I have to have things proportional, right? I have to have ratios that reduce to the same thing. Okay. Taylor Hart, what's one ratio that you would set up to try to figure out if these two lines were parallel? 9 over 24. Okay, and you want that to be the same as 9.75 over 26, right? Okay. Could he have done differently? Could he have done 9 over 9.75 and 24 over 26, or any combination of that, right? Okay, so just be aware, just because you're setting it up or trying to solve it differently, it doesn't mean you're wrong. Okay, what does this reduce to? 3 over 8. So I want this to reduce to what? 3 over 8, or 3/8. Okay, the problem is that decimal. You guys agree with that? That makes things a little interesting. When you get something like this, okay, now we all know that that's 3/4, right? Okay, but what do I multiply to get it to a whole? Sometimes that's a little bit more confusing. So, I want to show you a way that's going to work no matter what your decimal is. Isn't this the same as 9 3/4? Which, as an improper fraction, is what? 39 over 4. Everybody agree with that? 4 times 9 is 36, plus 3 is 9 over 4. Okay, so I have 39 over 4. That's still over 26 though, right? Okay, can I write 26 as a fraction? Okay, so what I'm doing, I changed one of them to a fraction, so I'm changing the other one to a fraction. Am I still okay? I haven't changed anything, I just rewrote it in a different way, correct? Okay. Doesn't this, right here, doesn't this mean I'm taking this fraction and I'm dividing it by this fraction? How do you divide by a fraction? You flip it and multiply by the reciprocal, right? So you multiply by 1 over 26 on the bottom, and 1 over 26 on the top. Well, on the bottom, just cancels out because you can cross-reduce. Okay, so you just cancel the entire bottom out. And now I'm left with this. Now, if I'm just multiplying two fractions, how do I multiply? Straight across. So 39 times 1 is 39. 4 times 26 is 104. Now I got to try to reduce. Okay, can I reduce this to 13 over 8? So let's try to find a number that goes into both of these. Immediately you see a 3, right? But does it go into here? Okay, so what's the next number that goes into 39, Travis? 13 goes into 39. Does it go into 104? I don't know. You might need a calculator to check.
8 times.
It goes into 39 how many? 3. 104? 8 times. Did my two ratios reduce to the same thing? Yeah. Is it going to take a little more work if it's a decimal? Yes. Travis? What's that? Oh, did I? Oops. Okay. Now, the decimals make it a little more challenging. Now, what I don't want you to do is I don't want you to go through this whole process if you don't have to. You with us, Amanda? Okay. If you have something like this, so you make it a little bit bigger. And I know I've mentioned this with at least a few of you, if not the whole class. Can I make that decimal into a whole number without changing it to a fraction? How, Royal? But you can't reduce it. You can't take anything out of both of those. And that's the biggest problem, is that it's a decimal. Taylor Stokes? Can't I double this? If I double this, what's that change to? 15 over 18. Okay, just make sure if you do it to the top, you got to do it to the bottom. Okay, and the reason why is because 2 over 2 is just 1, right? So am I actually changing my numbers, or am I just rewriting them in a different way? I'm just rewriting them. And then here I would reduce. I take a 3 out, and I get 5, 6. Is there any way you could have looked at this and be like, oh, that's 5, 6? No. You got to get rid of your decimal. Okay, get rid of your decimal, and then reduce. Just remember, a half should be easy for you. Just double the top and the bottom. If you have anything other than that, you might have to change it to a fraction. There's a few tricks, but the easiest way would just be to change it to a fraction and reduce. Okay? Doing all right, Tamaya? Okay. All right. Ready for our last two theorems? Okay, let's get through these things. This next one is one that you had to use on your worksheet packet to be able to finish it. Okay, and most of you just did it without even thinking, because we've been setting up proportions, so you knew somehow you had to set up a proportion. Okay, we'll go ahead and call this one 3 lines parallel. Okay, so automatically you should be looking for what if you think you're going to use this? 3 lines that are parallel. Okay. If 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally.
Like when you're up there writing all those, you can notice it's like first they'll be like, if 3 lines show them. Every time.
funny. At least you shouldn't have to look at the board, I guess.
Oh, at least I get it 2 times.
Okay. Now, does this say that your transversals have to be parallel? No. They do not. Maybe they are. They might be. But they don't have to be. Okay, so maybe they even cross in the diagram. Obviously, if they're not parallel, they're going to cross eventually. But maybe you can actually even see them cross. Okay, that's not a problem. Okay, so throw some letters in here. A, B, C, D, E, F, G. Okay. If you have 3 parallel lines going through 2 different transversals, then it divides the transversals proportionally. So, AB over BC would be equal to EF over FG. And any combination of that proportion, right?
Yes.
Yeah. Hey, there's a lot of different ways you can flip those letters around and still make a true proportion. Could you do AB over FG?
Oh, maybe.
No. This one's on the top. This one's on the bottom. This one's on the left. This one's on the right. Do they have anything in common? No. Okay, don't set those up over each other. Notice here you should be multiplying those, right? If you put them over each other, you're not going to be able to multiply them. Okay. So most of you probably actually used this already on your worksheet, okay, which is good. I kind of wanted to throw that at you. We'll talk about that a little bit more in a second. Okay, the next theorem, and the last one we have today, is a ray bisects a triangle. That was kind of the best name I could come up with for this one. It doesn't bisect the triangle completely. It just bisects an angle of the triangle. So if you want to write that as your name, that's fine. If you want to write a ray bisects an angle of a triangle, that's fine. I just wanted to keep it as short as possible. Okay, this theorem's a little bit longer. If a ray bisects an angle of a triangle, then it divides the opposite side into into segments whose lengths are proportional to the lengths of the other 2 sides. I know that's pretty long, but we'll get a diagram to go with that and it'll make a little more sense. Do we have that? Or most of it at least? Okay, so I have triangle A, B, C. Here's my angle that's being bisected. Now, does it say that it has to bisect this opposite side? No. Sometimes it might. Most of the time it probably won't. Okay, but it does say that it has to bisect an angle. Okay, so there's my angle bisector. If I have that, then it must be true that AD over DB is equal to AC over BC or CB. I'm going to change this to BD, so I'm in alphabetical order. Doesn't really matter though. Okay. Also, and then again, any combination of that, right? Could I do AD over AC? Yes, because we had that statement that said we can go horizontally also. So you could do AD over AC as well. And then it'd be BD over BC. Okay, just make sure you're setting up a proportion that's making sense to us. Alright, let's take a look here at example 3. I'm not going to go through this one just like I didn't go through example 1. Okay, but I do want to talk about it. Okay, obviously you look at that diagram, and is it going to be this theorem? No. It doesn't even look like it, right? It looks like my 3 lines parallel. Do you guys agree with that?
Yeah.
The problem is I don't have 3 parallel lines. Right?
That's a problem.
That is a problem. What did they give us that helps us with that problem, though?
The angles.
They showed me in example 3 that angles 1, 2, and 3 were all congruent, right?
Yeah.
McKenna, what do you know about those 3 angles? What type of angles are they? Okay, some of them are, not all of them. Travis? Corresponding, right? You agree with that, McKenna?
Yeah.
Those are corresponding angles. And it shows us they all have 1 tick mark, so they are congruent, right? What do you know about corresponding angles if they're congruent? What does that tell you? The lines are parallel. Can anybody name that theorem? Corresponding angles converse. It says if the corresponding angles are congruent, then the lines must be parallel. Does that take care of them not telling us the lines are parallel? Yeah. So now that I know the lines are parallel, Seth, can you set up a proportion to solve for TU? Can you do numbers for us, please? Yep. Okay, 9 over 15 equals 11 over x. And any combination of that proportion, right? Okay, we know our proportionality rules. Okay. Alright, the one I do want to talk about is like example 4, except I'm not going to do the one in your book. So make sure you get this down. Okay, this one's a good example to show you that that ray does not have to bisect the opposite side, does it? Okay, it bisects the angle. So I have A, B, C, D. Okay, perfect. Thank you. Okay, and then it tells us that this segment here is 3, this is 17, and this whole side is 15. We want to know what does CD equal, is our goal here. Okay, I don't know about you guys. I know some of you like to do this and some of you don't. But if they tell me I'm trying to find CD, the first thing I do is I find CD and I put an X in there. Okay? Because that tells me if I can just solve for X, I have my answer, right? I don't have to try to plug it in. I don't have to do that kind of stuff. So I put an X. I like to put an X right there because that tells me if I can find what X equals, then I'm done. Okay. Carson, what is a proportion based on our ray bisecting a triangle? What is a proportion I could set up? Just do the letters for me, please. Look at your theorem. Give me the letters though, like BC. Good. Okay. Is that an option? Okay. Personally, I'd have done BC over CD. Doesn't matter. No, because notice they're across from each other. Okay, that's good. Okay, so if I'd have done it differently, just check and see if they're across from each other or not, because they should be. Okay, so now I have this. So I can start filling things in. Well, AB is, it's what? 3. Over BC. That's where we come to a stopping point. Right, the whole thing is 15, right? And this part's X. So I must take 15 minus X to get what's left. So I have 15 minus X on the bottom equals AD is 17 over CD I know is X. That should be the challenging part for us, is getting it set up properly. From here, you should be able to solve this proportion, right? We've solved so many of these. You should be able to do this by now. 3 times X, 3X. When I multiply this way, do I multiply both of these? Yes. 15 times 7, 255. Negative X times 17, negative 17X. Add my 17X, right? And I get 20X equals 255. So X equals 255 over. Now looking at that, I know it's divisible by 5. 255 divided by 5 is, it's what, Taylor? 51. And 20 divided by 5 is 4. Again, I know I flew through that math, or that algebra portion of that, because we should be able to do that part by now. Okay, the challenging part should be setting up your proper proportion. Okay. Now really, we've been using a lot of this already other than that last theorem, right? We've basically been doing the same thing. Okay. So we're still working with proportions. Okay, not a lot has changed. We just added a few new theorems for that. How'd I do on time? A little slow. A little slow for this class, actually. Last class, the other classes had a little bit more time. All right, here we go. There's our assignment for tomorrow. Our chapter test is going to be in 4 class periods. So for us right now, that is Friday. Okay, so we have 8.7 left. We're going to do a day of Quizlet, and then we're going to do a chapter 8 review, and then we'll take our test. Okay?